Hello, students. This is Mr. Allen here, and today we're going to look at Chapter 5, Differential Equations and Slope Fields. Our objectives today is to use initial conditions to find particular solutions of differential equations and to use slope fields to approximate solutions of differential equations. And before we actually get into looking at some of these examples, I just need to say that, in Chapter 4, we've already looked at differential equations. Just to remind you, a differential equation is just an equation with a derivative. Oops, and I just wrote that incorrectly. Let me fix that. So dy dx equals, 2x plus 3 is a differential equation. It has a derivative, dy dx. It has an equal sign. It's an equation. This is a differential equation. You probably already know how to solve this. You would just integrate both sides. So that's what we're kind of dealing with here is differential equations. So in this section, we will learn that physical phenomena can be described by differential equations. We'll see that particularly next week. We know that a differential equation in x and y is an equation that involves an x and y and a derivative of y. A function y equals f of x is called a solution of a differential equation if the equation is satisfied when y and its derivatives are replaced by f of x and its derivatives. So for example, and this is important, differentiation and substitution would show, for example, that y equals e to the negative 2x is a solution for the differential equation y prime plus 2y equals 0. It can be shown that every solution of this differential equation has the form y equals ce to the negative 2x. Remember, our differential equation right here, any equation of this form, if you plug it into that equation, will make it true. This solution is called the general solution. And the reason it's called the general solution is basically the fact that C could be any number. Just like when we talk about, if we go back to the very first example here, if we solve this differential equation, we're going to get y equals x squared plus 3x plus c. This is the general solution because that plus c could be any number, so there's infinitely many curves. This is the same thing we're talking about here. Some differential equations have a singular solution and cannot be written as a special case of a general solution. Such solutions, however, are not considered in this section, and they're not very common. The order of the differential equation is determined by the highest order derivative in the equation. So, for example, this differential equation that we're talking about up here is a degree 1 differential equation. Here's another example. Y prime equals 4y is a first order differential equation. Here is a second order differential equation. S double prime of t is equal to negative 32. That sounds kind of familiar. S double t. I wonder if that's acceleration. So it has the following as a general solution. In other words, if we take this equation and we find its second derivative, it will be equal to that negative 32. Geometrically, and this is where we're going to start kind of thinking about slope fields, the general solution of a first order differential equation represents a family of curves known as solution curves. One for every value assigned to the arbitrary constant c. So if we look at our picture over here, by the way, I would like to note this is the differential equation. This is the general solution for that differential equation. We get 4 different curves. And you have to look carefully. There is a light blue curve, which is c equals negative 1. I'm sorry, c equals negative 2. There is a dark blue curve, which is when c is equal to negative 1. There is a dark black curve, which is c equals 1, and a dark black curve where c is equal to 2. All 4 of those curves are solutions to the differential equation. There are infinitely many of them. The particular solution, and this is what, your homework may ask what's the general solution, and if it's a general solution, you're going to have a C value with it. If they ask for the particular solution, they're going to give you something called the initial condition. We've already seen some examples of this in chapter 4. And what this initial condition is it's going to give you the value of both the dependent and the independent variable of the equation. The term initial condition stems from the fact that often in problems involving time, the value of the dependent variable or one of the derivatives is known as the initial time, t equals 0. So let's look at an example. Going back to the second derivative of s, that's position function. The second derivative of s equals negative 32. We could find the general solution, which turns out to be s of t equals negative 16t squared plus c sub 1t plus c sub 2. Suppose we have the following initial conditions. We know that, for example, that s prime of 0 is 64 and that s of 0 is 80. We can then substitute this information into our problem to figure out that the particular solution for this equation, or this differential equation, is negative 16t squared plus 64t plus 80. Now, let's do an actual example. Finding the particular solution. So here we have a differential equation, x, y prime, minus 3y equals 0, and we are asked to verify that y equals cx to the third is a solution. Then it says find the particular solution determined by the following given condition, initial condition. Now, the first question, there's two questions being asked here. The first question is just saying, hey, this is the solution. Check that it's the solution. So let's go ahead and do that first. We know that y equals cx to the third is a solution because the problem tells us that. We know that the derivative of that is y prime equals 3cx to the second. Now, if we look at the right-hand side of our equation, which is x, y prime minus 3y, we can now start substituting. Well, guess what we can put in for y prime? 3cx squared. What can we put in for y? Cx cubed, because that's what they are. So we make those substitutions, and we can clearly see that they are equal to 0, and that is exactly what the right-hand side is, 0. So we have just verified that that is indeed the solution. Now, I'd like to make a note here. Notice that nowhere in this problem did I do any integration. I did not integrate to get to this solution. They gave us the solution. We just needed to check the solution. Now, we need to figure out what the C value is based on the initial conditions. Y is 2 when x is equal to negative 3. So here's our general solution. So all we're going to do is we're going to substitute 2 in for y and negative 3 in for x. And when we work that out, it turns out that C is negative 2 over 27. And therefore, we'll substitute that back into our original solution, and we will get the final answer here of y equals negative 2x to the third over 27. That is the particular solution. A note, the general solution up there had just a C value there instead of that negative 2 over 27. So this is this first example. I've shown you how to verify a solution and how to find a particular solution. Okay, slope fields. So our second objective here is to look at slope fields. Solving a differential equation analytically can be difficult, even impossible. In other words, there's differential equations that you cannot solve analytically. However, there is a graphical approach that can be used, and it will help us learn a lot about the solutions of a differential equation. Consider the differential equation in the form y prime equals f of xy, where f of xy is some expression in x and y. At each point on xy in the xy plane, where f is defined, the differential equation determines the slope is y prime of f of xy of the solution at that point. If we draw short line segments, with the slopes of capital F of xy at the selected points in the domain of capital F, then these line segments form what we call a slope field, and I'll show you an example of that. By the way, another term that we use for slope field is directional field. Each line segment has the same slope as the solution curve through the point. A slope field shows the general shape of the solutions and can be helpful when giving a visual perspective of the directions of the solution in a differential equation. A solution curve of a differential equation y prime equals capital F of xy is simply a curve in the xy planes whose tangent line at each point xy has a slope equal to capital F of xy. So let's look at the following example. That should have said example 2, so I need to fix that. I'm sorry, this should be example 2. So here we have our differential equation. We're going to sketch a slope field for that differential equation. So, by the way, we cannot solve this differential equation the way it's written right now. You cannot integrate both sides because of that y on the right. But what we are going to do is we're going to use a slope field to sketch solutions that pass through the point 1, 1. So again, let me say this. We are not going to be able to solve this analytically. And since we can't do it analytically, we're going to have to try something different. So remember, our equation here is y prime equals 2x plus y. That's written right here in the table. So we can just make a table of values. So when x is -2 and y is -1, if we plug those into here, we're going to get -2 times 2 plus -1, that's -5. So that tells us the slope of the tangent line at -2, -1 is -5. Similarly, if we plug in the points, let's say 0, 1, 0 for x and 1 for y, that's just going to give us a slope of 1. Now, we take all this information in this table, and now we can create what's called a slope field. This is a slope field. It gives us a lot of information about what the solution is for that particular differential equation. Now, we don't know what the actual equation is. We don't know what y is, but we know based on this slope field, it gives us some idea of what the solutions for that particular differential equation will be. Now, remember, we're interested in finding the solution at 1, 1, okay? The point 1, 1. So that's 1 to the right on the x-axis and up 1 on the y-axis. So what we can do then is we can take that slope field, and I've already got it drawn here in black, but that dark curve there, you'll notice the point 1, 1 is on that curve. You see how the curve kind of goes along with the slopes of those blue individual slopes from the slope field? It gives you some idea of what that curve looks like. So this is the particular solution for the differential equation y prime equals 2x plus y. Okay. And that is that.